And now in this lecture we find out the area of a circle. In the drawing we have quadrilateral ABCD. Inside this quadrilateral we have a circle. In addition, we know that side AB of this quadrilateral equals to 2 units, side BC equals to 8 units, and side DC also equals to 8 units. This is angle ABC that is equals to 90 degrees, and this angle DCB also equals to 90 degrees in its side. Again, our mission is to find out the area of this circle. Okay, so first of all, we'll do a construction. That is to say, we'll extend side DA and side CB of this quadrilateral by a straight line until they touch each other. This is their touching point. We define the touching point as point M. By doing this construction, we created the right big triangle, triangle DCM. We define this angle as theta. And we focus on the right big triangle, triangle DCM that we created here. In this big right triangle DCM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Okay, so in the next step, we focus on, we have here BC, line segment BC. Line segment BC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. Then when we extended the straight line BC by straight line, the result is CM. So actually, when you extend a straight line by straight line, the result must be a straight line, therefore CM is one straight line. So we focus on the upper side of the straight line CM at point B. Here, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees, because the missing angle is actually angle ABM. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that I mentioned. Therefore, the missing angle here, angle ABM, must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles on the upper side of the straight line CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees. So, if this angle equals to 90 degrees, it means that triangle ABM, the small triangle ABM, is a right triangle. So, we'll focus on the right small triangle ABM. This small right triangle ABM, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. In the next step, we prove that the right big triangle, triangle DCM that we created here, is similar to the right small triangle, triangle MBA. So I write it down. We prove the right big triangle DCM is similar to the right small triangle, triangle MBA. So, why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. Actually, this is the angle DCM, in the right big triangle DCM, and it is equal to this angle, that is actually angle ABM, in the right small triangle MBA. Repeat again. Angle DCM in the right big triangle CDM equals to the angle ABM in the right small triangle MBA. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is actually a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle theta, as it belongs to the big right triangle DCM, it will be defined as angle DMC. And if we relate to angle theta as it belongs to the right small triangle, triangle MBA, then it will be called angle AMB. Repeat again. This equation means that angle theta equals to itself. We just call two angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually this is the angle MDC. In the right big triangle CDM, and it is equals to this angle, that is actually angle MAB in the right small triangle MBA. Repeat again. Angle MDC in the big right triangle CDM equals to angle MAB in the right small triangle MBA. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually prove that all the three angles in the big right triangle CDM are correspondingly equal to all the three angles in the right small triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right big triangle CDM is similar, this is the sign of similar, to the right small triangle MBA. According to angle similarity rule. And from the fact those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side DC in the big right triangle DCM over side AB in the right small triangle MBA equals to side CM in the big right triangle CDM over side BM in the right small triangle MBA. Repeat again, we derive that DC over AB equals to CM over BM. DC is 8 over AB. AB is 2. And it is equals to CM over BM. CM in total it is equals to CB plus BM. That is to say CM equals to CB, that is 8, plus BM, that is the missing side. So in total CM equals to 8 plus BM. So we solve the CM here by 8 plus BM divided by BM. In conclusion, found out that 8 over 2 equals to 8 plus BM over BM. 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here we multiply this equation by BM, and we get that 4 times BM equals to 8 plus BM. Here we subtract BM from this equation, and we get that 4BM minus BM is 3BM is equals to 8. Here we divide this equation by 3, and finally we get that BM equals to 8 over 3 units in its length. Okay. Side BM equals to, this side BM equals to 8 over 3 units in its length. In the next step, we focus on this small right triangle MBA, and we'll implement the Pythagoras theorem in this right triangle MBA in order to find out the length of the hypotenuse AM. That is the only missing side here. So, in the right triangle MBA, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse in the right triangle MBA is AM, therefore the square of the hypotenuse is AM squared. This equals to AB squared plus BM squared. Repeat again. According to the Pythagoras theorem, AM squared equals to AB squared plus BM squared. Here by PT is the version for Pythagoras theorem. So AM squared, that is the square of the hypotenuse, equals to AB squared. AB is 2, therefore AB squared is 2 squared, that is 4, plus BM squared. Just like now found out that BM equals to 8 over 3, therefore BM squared is 8 over 3 squared. 8 over 3 squared is 64 over 9. So in conclusion, found out that AM squared equals to 4 plus 64 over 9. So AM squared equals to, here we have 4 plus 64 over 9. We will multiply 4 by 9 and then we divide it by 9 in order to account factor with 64 over 9. 4 times 9 is 36, so in total in the numerator of this expression we will have 36 plus 64 over 9. 36 plus 64 is 100 divided by 9. In conclusion, we found out that AM squared equals to 100 over 9. Here we will take a root out of this equation and we get that AM equals to the square root of 100 over 9. So AM equals to the square root of 100 over 9. And the square root of 100 over 9 is equals to the square root of 100, that is 10, over the square root of 9, that is 3. So in conclusion, we found out that AM equals to 10 over 3 units in its length. The hypotenuse AM equals to 10 over 3 units. AM equals to 10 over 3 units in its length. In the next step, we will do another construction. That is to say, we will draw perpendicular on side BC. We will draw the perpendicular in such a way on side BC that the perpendicular on BC will be also tangent to this circle. It is absolutely possible to do it because we can draw the perpendicular on BC on infinite different points on BC. In each point we can draw the perpendicular. Therefore, we will choose the perpendicular in the point on BC in such a way that the perpendicular on BC will be also tangent to this circle. Okay. So actually this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular inside BC as T. We will define the point of tendency of the perpendicular in the circle as point K. In the next step, we will extend the perpendicular TK until it touches side AD. We define the touching point of the extended perpendicular TK with side AD as point L. By doing this construction, we created here the right middle triangle, triangle MLT. Inside this right middle triangle, triangle MLT, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. In the next step, we define the center of this circle, this point as O. We define the point of tendency of tangent BT with this circle as H. And finally, we define the point of tendency of tangent AB with this circle as N. In the next step, we join points O and A together by a straight line. Here point O is the center of the circle, point H is the point of the circle itself, therefore OH is the radius of this circle. We define the radius of this circle as x, therefore OH is the radius of the circle is equal to x according to our definition. We can implement here rule 1. I repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle and also tangent AB that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. We can actually implement this rule 1 in our drawing. Why? Because in our drawing we have the radius OH that is drawn to point H, that is the point of tendency of tangent BT with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius HO. If BT is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and K together by a straight line. Line segment OK, this line segment OK is the radius of this circle that is equal to x. Again, we have here the radius OK that is drawn to point K. Therefore, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and N together by a straight line. Line segment ON is the radius of this circle that is equal to x. Again, we have the radius ON that is drawn to point N. Therefore, according to rule 1, this angle equals to 90 degrees, and this angle will also equal to 90 degrees. In the next step, we focus on this small quadrilateral OKHT. In this small quadrilateral OKHT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the missing fourth angle. In total, they must be equal to 360 degrees. According to the rule, that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles in this quadrilateral OKHT to 360 degrees, the missing angle must be equal to 90 degrees. So inside quadrilateral OKHT we have 4 right angles. Therefore, this quadrilateral must be at least a rectangle, if not a square. So we relate to this quadrilateral OKHT as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, side OK equals to side HT. But OK is x, therefore HT must be also equal to x units in its length. Likewise, according to the sum rule, rectangle OKHT, side OK must be equal to the opposite side KT. But OH is x, therefore KT must be also equal to x units in its length. So actually we found out that quadrilateral OKHT, this small quadrilateral, is not a rectangle but a square. Why? Because all of its sides are equal to each other. Its side equal to x. We repeat on the same process on this small quadrilateral and OBH. Inside this small quadrilateral we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, this quadrilateral NOBH that has four right angles, we relate to it as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side ON must be equal to the opposite side B in rectangle ON BH. But ON equals to x, therefore BH must be also equal to x. Likewise, according to the same rule, side OH must be equal to the opposite side NB in rectangle OH B in rectangle ON BH. OH must be equal to NB, but OH is x, therefore BH. OH is x, therefore NB must be also equal to x units in its length. Again, we found out that quadrilateral ON BH is not a rectangle but a square. In conclusion, we found out that BT in total equals to x plus x, that is 2x. So line segment BT equals to 2x units in its length. So I write it down. Line segment BT equals to 2x units in its length. In the next step, we will prove that the right middle triangle LTM, this right triangle LTM, is similar to the right small triangle MBA. Okay, the right middle triangle LTM is similar to the right small triangle MBA. So right, the middle triangle is similar to this small triangle MBA. First of all, we have those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually, this is the angle LTM in the right middle triangle LTM, and it is equal to this angle, this is actually angle ABM in the right small triangle MBA. Repeat again. Angle LTM in the right middle triangle LTM equals to angle ABM in the right small triangle MBA. They are both equal to 90 degrees, therefore they are equal to each other. In addition, we have this is angle theta, that is a common angle, it belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the right middle triangle LTM, it will be defined as angle LMT, and it equals to itself. So if we relate to angle theta as it belongs to the right small triangle MBA, it will be called angle AMB. Repeat again. Angle LM. This equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually this is angle MLT in the right middle triangle LTM, and it is equal to this angle. This is actually angle MAB in the right small triangle MBA. Repeat again. Angle MLT in the middle right triangle LTM equals to angle MAB in the right small triangle MBA. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually proved that all the three angles of the right middle triangle LTM are correspondingly equal to all the three angles of the right small triangle MBA. Therefore, those two right angles are similar to each other according to angle similarity rule. So I write it down. We actually prove that the right middle triangle LTM is similar. Again, this is the sign of similar to the right small triangle MBA, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LT of the right middle triangle LTM over side AB of the right small triangle MBA equals to side TM of the right middle triangle LTM over side BM of the right small triangle MBA. Repeat again. We derive that LT over AB equals to TM over BM, and also it is equals to side LM, that's actually the hypotenuse of the right middle triangle LTM, side LM over side AB, that's actually the hypotenuse of the right small triangle MBA. And again, it is equals also to LM over AM. So in conclusion, we found out that LT over AB equals to 2M over BM, and it is also equals to LM over AM. Here we have side LT is the missing side, so we leave it as it is, over AB. AB equals to 2, so we substitute AB by 2, and it is equals to side TM. Here, TM, from the drawing, it is very easy to see that TM equals to TB plus BM. That is to say, TM equals to TB, that is 2x, plus BM, that is 8 over 3. So in total, TM equals to 2x plus 8 over 3. Yeah. Tm equals to 2x plus 8 over 3 divided by Bm. Here Bm equals to 8 over 3. And it is also equals to Lm. Lm equals to La plus Am. That is to say, Lm equals to La, that is the missing side, plus Am, that is 10 over 3. So in total, Lm equals to La plus 10 over 3. So here, Lm equals to La plus 10 over 3 divided by Am. AN equals to 10 over 3. So in conclusion, found out that LT over 2 equals to 2x plus 8 over 3 over 8 over 3, and it is also equals to LA plus 10 over 3 over 10 over 3. So we focus on this long equation. In this long equation, those two sides are equal to each other. Therefore, we create equation 1 from those two sides that are equal to each other. So according to equation 1, LT over 2 equals to 2x plus 8 over 3 over 8 over 3. So according to equation 1, LT over 2 equals to, here we have 2x plus 8 over 3. So we will multiply 2x by 3, then we divide it by 3 in order to have a common factor with 8 over 3. So 2x times 3 is 6x, so in total in the numerator of this expression we will have 6x plus 8 divided by 3, and we have to divide it also by 8 over 3. We focus on this side of the equation 1. On this side of equation 1, we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. What is left from equation 1 after we cancelled 3? In this side of the equation, we have LT over 2 is equals to, on the other side of the equation, we have 6x plus 8 over 8. So here we cross multiply this equation, equation 1, and we get that according to equation 1, 8 times LT equals to 2 times 6x plus 8. So here we divide this equation, equation 1 by 2, and we get that according to equation 1, 8 over 2 is 4, so in total in this side of the equation we have 4LT is equals to, here 2 over 2 is 1, so we left only here, in the other side of the equation we left with 6x plus 8. So here we divide this equation, equation 1 by 4, and finally we get that LT equals to 6x over 4 is 1.5x, plus 8 over 4 is 2, so it is plus 2. So in conclusion, we found out that LT equals to 2 plus 1.5x. Okay. Here, this line segment LT or side LT equals to 2 plus 1.5x. We'll continue to focus on the long equation that we created here. In this long equation, those two sides are also equal to each other. Therefore, we will create equation 2 from those two sides that are equal to each other. So according to equation 2, we have 2x plus 8 over 3 over 8 over 3 equals to LA plus 10 over 3 over 10 over 3. Again, according to equation 2, 2x plus 8 over 3 over 8 over 3 equals to LA plus 10 over 3 over 10 over 3. So in this side of equation 2 we have 2x plus 8 over 3. So here we will multiply 2x by 3 and then we divide it by 3 in order to have a common factor with 8 over 3. And we get that 2x times 3 is 6x. So in the numerator in total we will have here 6x plus 8 divided by 3, and we have to divide it also by 8 over 3. On the other side of equation 2, this equation 2, we have LA plus 10 over 3. So here we multiply LA by 3 and then we divide it by 3 in order to have a common factor with 10 over 3. So LA times 3 is 3LA. So in total, in the numerator of this expression we have 3LA plus 10 divided by 3, and we have also to divide it by 10 over 3. So in this side of equation 2 we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. In the other side of this equation 2 we have 3 in the numerator and 3 in the denominator, so 3 also will get cancelled. So what is left of this equation 2, after we cancelled 3 on both sides of the equation, what is left is in this side of the equation 2 we left only with 6x plus 8 over 8. This equals to, in the other side of the equation we left only with 3LA plus 10 over 10. So here we must multiply this equation 2, and we get that according to equation 2, ten times 6x plus 8 equals to 8 times 3LA plus 10. Here we divide this equation 2 by 2. And finally we get that according to equation 2, 10 over 2 is 5, and inside the brackets we have 6x plus 8 equals to 8 over 2 is 4, and inside the brackets we have 3LA plus 10. So here we'll open the brackets on both sides of this equation 2, and we get that according to equation 2, 5 times 6x is 30x, plus 5 times 8 is 40. This equals to 4 times 3LA is 12LA, plus 4 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled. After cancel is 40, we left only with, in this side of the equation, we left only with 30x. That equals, in the other side of the equation, we left only with 12LA. So according to equation 2, 30x equals to 12LA. Here we divide this equation 2 by 12. And finally, we'll get that LA equals to 30x over 12, that is 2.5x. Okay, so the length of this 97 LA equals to 2.5x. In the next step, I will copy this small quadrilateral ABTL with the circle that is described inside it. I will copy it to a new page, and we'll actually implement rule 2 in this small quadrilateral ABLT. So actually this is the small quadrilateral ABLT with the circle that is inscribed inside it, that I copied from the original drawing. Here we will define the point of tendency of tangent AL with this circle as K. We will define the point of tendency of tangent AB with this circle as M. We will define the point of tendency of tangent BT with this circle as N. And finally, we will define the point of tendency of tangent LT, this tangent LT with this circle as H. In the next step, we will focus on the common external point, point A. This point, common external point, point A. And we'll implement here rule 2. I'll remind you quickly what is rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing we have a circle and the common standpoint point P. From the common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2 they are equal to each other. That is to say PA equals to PB. We can actually implement this rule 2 in our drawing. Why? Because if you focus on the common external point A, from the common standpoint point A, we have two tangents to this circle, tangent AK and tangent AM, and according to rule 2 they are equal to each other. So I write it down. AK, tangent AK equals to tangent AM in its length, according to rule 2. So if we define the length of tangent AK as A, then the length of tangent AM must be also equal to A because they are equal to each other. So in conclusion, we found out that AK equals to AM equals to A. In the next step, we will focus on this common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BN and tangent BN. Again, tangent BN and tangent BN. And according to rule 2, they are equal to each other. That is to say, BN equals to BN. BN equals to BN. So actually, if we define the length of tangent BM as B, then tangent BN must be also equal to B because they are equal to each other. So in conclusion, we found out that BN equals to BM equals to B. In the next step, we will focus on this common external point, point T. From the common external point, point T, from the common external point, point T, we have two tangents to this circle, tangent TH and tangent TN. And according to rule 2, they are equal to each other. This is to say TH equals to TN. TH equals to TN. So if we define the length of tangent TH is C, then the length of tangent Tn must be also equal to C because they are equal to each other. So in conclusion, we found out that Th equals to Tn equals to C. And finally, we'll focus on this common exam point, point L. From the common exam point, point L, we have two tangents to this circle, tangent LK and tangent LH, and according to rule 2, they are equal to each other. That is to say, LK equals to LH. LK equals to LH. According to the same rule, rule 2. So if we define the length of tangent LK as D, then the length of tangent LH must be also equal to D because they are equal to each other. So in conclusion, we found out that LK equals to LH equals to D. In the next step, we will add side AB to the opposite side, side LT. So what is the value of AB, side AB plus plus the opposite side, side LT? From drawing, it is very easy to see that AB equals to A plus B and LT equals to C plus D. So in total, AB plus LT equals to A plus B plus C plus D. Likewise, we will add side AL to the opposite side, side BT. So what is the value of side AL plus side BT? From the drawing, it is very easy to see that AL plus BT in total equals to A plus B plus C plus D. Again, AL plus BT equals to A plus B plus C plus D. So AL plus BT equals to also to A plus B plus C plus D. So those two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. That is to say, AB plus LT equals to AL plus BT. So I write it down. AB plus LT equals to AL plus BT. Repeat again. Therefore, we found out that AB plus LT equals to AL plus BT. AB is 2, so we substitute AB by 2 plus LT. We have already found out that the length of line segment LT is 2 plus 1.5x. Therefore, we substitute LT in this equation by 2 plus 1.5x, and it is equals to AL. Here AL is 2.5x, therefore we substitute AL here by 2.5x plus BT. Here BT equals to x plus x, that is 2x. So BT equals to 2x, therefore we substitute BT in this equation by 2x. So in conclusion, we found out that 2 plus 2 plus 1.5x equals to 2.5x plus 2x. 2 plus 2 is 4. So in total, this equation we have 4 plus 1.5x. That equals to 2.5x plus 2x equals to 4.5x. So in total, we actually found out that 4 plus 1.5x equals to 4.5x. Here we subtract 1.5x from this equation, and finally we get that 4 equals to 4.5x minus 1.5x is 3x. So if we found out that 4 equals to 3x, here we divide this equation by 3, and finally we get that x equals to 4 over 3 units in its length. Okay. So we found out actually that the radius x of this circle equals to 4 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle will be equal to pi times the radius squared. The radius is x, therefore the radius squared is x squared. So the area of our circle equals to pi x squared. And we just right now found out that x equals to 4 over 3. If x equals to 4 over 3, it means that x squared equals to 4 over 3 squared. So the area of our circle will be equal to pi times 4 over 3 squared. This is x squared. So the area of our circle will be equal to, we have pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. Repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the area of this circle. So, in the drawing, we have quadrilateral ABCD. Inside this quadrilateral, we have this circle. In addition, we know that side AB equals to 2 units in its length, side BC equals to 8 units, and side DC also equals to 8 units. This is angle ABC, this is equal to 90 degrees in its side, and this is angle DCB, that is also a right angle. Again, our mission is to find out the area of this circle. So, in the first step, we did a construction. That is to say, we extended side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. This is their touching point, and we defined the touching point of the extended side DA and the extended side CB as M. By doing this construction, we created the right big triangle, triangle DCM. On the right big triangle, triangle DCM, we define this angle as theta, and we focus on this right big triangle DCM. So in this right triangle DCM, this angle equals to 90 degrees, this angle equals to theta according to our definition. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Okay, then we focused on this line segment BC. Line segment CB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. Then we extended the straight line CB by straight line, and the result is CM. When you extend the straight line by straight line, the result must be a straight line. So CM must be a straight line. So if we focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. For which angles we have at the upper side of CM at point B, we have this angle that is equal to 90 degrees, plus the missing angle that is actually angle ABM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles of the upper side of CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees. And therefore, the small triangle ABM is a right triangle, because this angle equals to 90 degrees. So in the small right triangle ABM, this angle equals to 90 degrees. This angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. Then we proved that the right big triangle DCM is similar to the right small triangle MBA. Well, those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, this is angle theta, that is a common angle, it belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we have proved that all the three angles of the right big triangle DCM are correspondingly equal to all the three angles of the right small triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side DC in the big right triangle DCM over side AB in the small right triangle MBA equals to side CM in the big right triangle DCM over side BM in the right small triangle MBA. Repeat again. We will derive that DC over AB equals to CM over BM. DC is 8, AB is 2, and it is equal to CM over BM. CM, from the drawing, it is very easy to see that CM in total equals to CB plus BM. That is to say, CM equals to CB, that is 8, plus BM. So in total, CM equals to 8 plus BM. Here, CM equals to 8 plus BM, and we have to divide it by BM. So in conclusion, we found out that 8 over 2 equals to 8 plus BM over BM. 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here we multiply this equation by BM and found out that 4 times BM equals to 8 plus BM. Here we subtracted BM from this equation and found out that 4BM minus BM is 3BM, so 3BM equals to 8. Here we divided this equation by 3 and finally found out that BM equals to 8 over 3 and itself. Here, this side BM equals to 8 over 3 and itself. Okay, then we implemented the Pythagoras theorem on the right small triangle, triangle MBA. On the right small triangle MBA, according to the Pythagoras theorem, AM square equals to AB square plus BM square. I repeat again. On the right small triangle MBA, in the right small triangle MBA, AM square equals to AB square plus BM square. So AM square, that is the square of the hypotenuse, equals to AB square. AB is 2, therefore AB square is 2 squared, that is 4, plus BM square. BM is 8 over 3, therefore BM square is 8 over 3 square. BM is 8 over 3, therefore BM square is 8 over 3 squared, that is 64 over 9. So in conclusion, we found out that AM square equals to 4 plus 64 over 9. Here we multiplied 4 by 9 and then we divided by 9 in order to have a common factor with 64 over 9. So 9 times 4 is 36. In total, in the numerator we will have 36 plus 64 divided by 9. 36 plus 64 is 100 divided by 9. So in conclusion, we found out that AM square equals to 100 over 9. Here we took a root out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 over 9 is the square root of 100, that is 10, over the square root of 9, that is 3. So in total, found out that the hypotenuse AM equals to 10 over 3 is inside. Here, AM equals to 10 over 3 is inside. In the next step, we did another construction, that is to say, we draw perpendicular on side BC in such a way that the perpendicular on BC will be also tangent to this circle. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular inside BC as T. We define the point of tendency of the perpendicular with this circle as K. Then we extended the perpendicular TK by side line until it touches side DA. We define the touching point of the extended TK with side DA as L. By doing this construction, we created the right middle triangle, triangle LTM. In the right middle triangle LTM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. Okay. Then we defined the center of this circle as O, and we defined the radius of this circle as X. Then we join points O and H together by a straight line. Point O is the center of the circle, point H is the point of the circle itself, therefore OH is the radius of this circle that is equal to X, according to our definition. The radius OH is drawn to point H, that is the point of tendency of tangent BT with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius HO. If BT is perpendicular to HO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. Likewise, we join points O and N together by straight line. ON is the radius of this circle, that is equal to X. The radius ON is drawn to point N, therefore according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Likewise, we join points O and K together by straight line. Line segment OK is the radius of this circle, that is equal to X. The radius of K is drawn to point K, therefore, according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then we focus on this small quadrilateral OKHT. In this small quadrilateral OKHT, we have 1, 2, 3 angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral OKHT, we have 4 angles. Therefore, we relate to this quadrilateral as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, OK equals to HT. But OK is X, therefore HT must be also equal to X. Likewise, according to the same rule, OH must be equal to KT. But OH is X, therefore KT must be also equal to X. So actually found out that quadrilateral OKHT is not a rectangle but a square. Then we did the same process here. Repeated the same process here. Inside this small quadrilateral ONBH, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral ONBH, we have 4 angles. And we know that the opposite, therefore we can relate to this quadrilateral as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side ON equals to side HB. But ON is X, therefore HB must be also equal to X. Likewise, according to the same rule, side OH must be equal to side NB in rectangle ONBH. But OH equals to X, therefore NB must be also equal to X. Again, we found out that quadrilateral ONBH is not a rectangle but a square. In conclusion, we found out that BT in total equals to X plus X, that is 2X. Okay, again here, BT equals to 2X units in length. Then we proved that the right middle triangle LTM is similar to the right small triangle, triangle MBA. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I shall prove that all the three angles in the right middle triangle LTM are correspondingly equal to all the three angles of the right small triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that LT over AB equals to TM over BM equals to LM over AM. LT is the missing side, so we will leave it as it is, over AB. AB is 2, so we substitute AB by 2. What is the value of TM? Here from the drawing it is very easy to see that TM equals in total to 2x plus 8 over 3. So we substitute TM by 2x plus 8 over 3 divided by BM. BM is 8 over 3, therefore we substitute BM by 8 over 3 and it is equals to LM. LM in total equals to LA plus AM. That is to say LM in total equals to LA, that is the missing side, plus AM, that is 10 over 3. So in total LM equals to LA plus 10 over 3. Here LM equals to LA plus 10 over 3 over AM. AM equals to 10 over 3, so we substitute AM here by 10 over 3. So in conclusion, we found out that LT over 2 equals to 2x plus 8 over 3 over 8 over 3, and it is also equals to LA plus 10 over 3 over 10 over 3. Those two sides are equal to each other, so we created equation 1 from those two sides that are equal to each other. According to equation 1, LT over 2 equals to 2x plus 8 over 3 over 8 over 3. So in this side of the equation we have 2x plus 8 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to become a factor with 8 over 3. And found out that 2x times 3 is 6x. So in total in the numerator of this expression we will have 6x plus 8 divided by 3, and we have to divide it also by 8 over 3. So in this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 we get cancelled. After we cancel 3, we left only with LT over 2, that equals to 6x plus 8 over 8. Here we cross multiply this equation and found out that 8 times 3LT equals to 2 times 6x plus 8. Here we divided this equation by 2 and found out that 8 over 2 is 4, so in total on this side of the equation we have 4LT. This equals to 2 over 2 is 1, so in total this side of the equation we left only with 6x plus 8. So in conclusion found out that 4LT equals to 6x plus 8. Here we divided this equation by 4 and finally found out that LT equals to 6x over 4, that is 1.5x. Plus 8 over 4, that is 2. So in conclusion, found out that LT equals to 2 plus 1.5x. Here LT, 9 segment LT equals to 2 plus 1.5x. Then continue to focus on this log equation. Those two sides they are equal to each other, therefore we created equation 2 from those two sides that are equal to each other. According to equation 2, we actually found out that 2x plus 8 over 3 over 8 over 3 equals to LA plus 8 and 10 over 3 over 10 over 3. So in this side of the equation we have 2x plus 8 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to become a factor with 8 over 3. 2x times 3 is 6x, so in total in the numerator of this expression we have 6x plus 8 divided by 3, and we have to divide it also by 8 over 3. In this side of the equation we have LA plus 10 over 3. Here we multiply LA by 3 and then we divide it by 3 in order to have a common factor with 10 over 3. 3 times LA is 3LA, so in total the numerator of this expression we have 3LA plus 10 divided by 3, and we have to divide it also by 10 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. In the other side of the equation we also have 3 in the numerator and 3 in the denominator, so 3 will also be cancelled. So what is left from this equation 2 after we cancel 3 on both sides of the equation? What is left is actually 6x plus 8 over 8 equals to 3 times LA plus 10 over 10. Here we cross multiply this equation 2, and found out that 10 times 6x plus 8 equals to 8 times 3LA plus 10. Here we divided this equation 2 by 2, and finally found out that 10 over 2 is 5. Inside the brackets we have 6x plus 8, and here we have 8 over 2 is 4, and inside the brackets we have 3LA plus 10. Here we open the brackets on both sides of the equation and found out that 5 times 6x is 30x plus 5 times 8 is 40. That is equals to 4 times 3LA is 12LA, and plus 3 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled, and we left only with 30x, that is equals to 12LA. Here we divided this equation by 12, and finally found out that LA equals to 30x over 12, that is 2.5x. So here LA equals to 2.5x in its side. Then I copied this small quadrilateral ALBT with its circle that is described inside it in a new page, and we implemented rule 2 in this quadrilateral ALBT. This is actually the small quadrilateral ALBT that I copied from the original drawing with the circle that is described inside it. And here we focus on the common standpoint point A. From the common standpoint point A, we have two tangents to this circle, tangent AK and tangent AM. And according to rule 2, they are equal to each other. So AK equals to AM according to rule 2. So if we define the length of a edge as A, then AM must be also equal to A because they are equal to each other. So in conclusion, we found out that AK equals to AM equals to A. Then we focus on the common standpoint point B. From the common standpoint point B, we have two tangents to this circle, tangent BM and tangent BN. And according to rule 2, they are equal to each other. That is to say, BM equals to BN. BM equals to BN. So if we define the length of BM as B, then the length of BN must be also equal to B because they are equal to each other. So in conclusion, we found out that BN equals to BM equals to B. And then we focus on the common standpoint point T. From the common standpoint point T, we have two tangents to this circle, tangent Tn and tangent Th. And according to rule 2, they are equal to each other. That is to say, Tn equals to Th according to rule 2. So if we define the length of Tn as C, then the length of Th must be also equal to C because they are equal to each other. So in conclusion, we found out that Th equals to Tn equals to C. And finally, we focus on the common standpoint point L. From the common standpoint point L, we have two tangents to this circle, tangent LK and tangent LH, and according to rule 2, they are equal to each other. That is to say, LK equals to LH. So if we define the length of LH as D, then the length of, if we define the length of LK as D, then the length of LH must be also equal to D because they are equal to each other. So in conclusion, we found out that LK equals to LH equals to D. Then we added side AB to side LT. What is the value of AB plus LT? From the drawing, it is very easy to see that AB equals to A plus B and LT equals to C plus D. So in total, AB plus LT equals to A plus B plus C plus D. Likewise, we added side LT to the opposite side, side BT. What is the value of AL plus BT? From the drawing, it is very easy to see that AL plus BT in total equals to A plus B plus C plus D. Again, AL plus BT equals to A plus B plus C plus D. So AL plus BT also equals to A plus B plus C plus D. So those two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. That is to say, AB plus LT equals to AL plus BT. AB is 2 plus LT. We already found out that LT equals to 2 plus 1.5x, therefore we substitute LT by 2 plus 1.5x, and it is equals to AL plus BT. AL equals to 2.5x, therefore we substitute AL here by 2.5x plus BT. Here BT equals to x plus x, that is 2x, so we substitute BT by 2x. Here we substitute BT in this equation by 2x. So in conclusion, found out that 2 plus 2 plus 1.5x equals to 2.5x plus 2x. 2 plus 2 is 4, so in total in this side of the equation we have 4 plus 1.5x. That is equal to 2.5x plus 2x, that is 4.5x. So in conclusion, found out that 4 plus 1.5x equals to 4.5x. Here we subtracted 1.5x from this equation, and finally found out that 4 equals to 4.5x minus 1.5x is 3x. So in conclusion, found out that 4 equals to 3x. Here we divided this equation by 3 and finally found out that x equals to 4 over 3 units in its length. So the radius x equals to 4 over 3 units in its length. Our mission is to find out the area of this circle. We know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle equals to pi times the radius squared. The radius is x, therefore the radius squared is x squared. So the area of our circle is pi x squared. We just right now found out that x equals to 4 over 3. If x is 4 over 3, then x squared is 4 over 3 squared. Therefore, this expression will be equal to pi times 4 over 3 squared. Pi times 4 over 3 squared equals to pi times 4 over 3 squared. 4 over 3 squared is 4 squared, that is 16, over 3 squared, that is 9. So actually found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, the area of this circle equals to 5.585 square units. Okay, thank you very much.